Okay, welcome back. Hopefully lunch was good to you. It was good to me. I know that. So our next session is with Daryl Paul from Better Thermal Resistance Board, BTR Board. Daryl is truly a guru about installation and performance in wall systems. And he's going to share some questions and thought-provoking ideas about condensation at the windowsills. So Daryl, I'll leave it to you.
Thanks, Terry. So this comment or this concern came up when I was sitting on the CSA 440 committee and we were talking about the new standard, the 2024 standard. We got it all finished and then it never got put into the 25 code. So we were talking about what do we do with wood frame walls and how do we protect the sills? So I said, well, why don't I just put a code change in, thinking this was a simple process, right? You just write something up, send it in, and then you sit on 50 committees and spend 100 hours. So it's a simple process, but it got through the code, and that's what precipitated this, is because it was all about what happens when you put a sill pan in at the bottom, and then you want to insulate that window to try and drain moisture out of it. So when we look at some of the myths and mechanisms behind windows, one of the myths on windows is they don't leak. So if you've ever heard Steebrook or Straub talk about windows, there's two types of windows, those that leak and those that will leak, right? But from my experience, I spent 30 years as an envelope technician. I ran an envelope engineering company, and we would test windows. And when we tested windows, what we found was that probably over 55% of the leaks in windows actually came from another source. It came in the soffits, it came in the upper window, it came in from a deck, it came from somewhere else, and it just showed up on the window below. Well, that tells us that the water gets in that window, it runs around the rough opening, and it sits on the bottom on a horizontal surface. And what do we learn about tar paper on horizontal surface? You know, a 30-minute tar paper is good for 30 minutes, a 60 is good for 60. A house wrap, what about the corners? So we just don't have the protection there. Anybody that's renovated knows what the window looks like when you pull that out and the damage that's occurring. So this discussion is all about what is the effect of that lower sill in terms of draining the water, but also the insulation value that needs to be in that lower sill and how the code change has affected that. So some of the other things, we should seal four sides, true or false? Right? A lot of people feel that a window shouldn't leak, and if we seal four sides, that eliminates the water getting in, but it also stops it from getting out. If you look at drainage not required, what about doors that don't need the 3/8 space below? So I framed for 12 years at the start of my career. We always had to put the little shim under the window, and I was told that was for insulation. How come we don't need it under doors? We always set the doors right on the bottom, and there was no space for insulation. Does that mean doors are better insulated? No. It means our perception of what is happening there is totally different than what reality is. So these are some of the myths. So if we compare that to the mechanisms that we need to look at when we install a window, particularly in a building that is sensitive to moisture like wood, whether it's a single family, a multifamily, an apartment, 6-story, doesn't matter. If it's sensitive to wood, we need to control those 4 layers: water, air, thermal, and vapor. And what's the most important one? Well, we need to deal with water. And why? Because wood is the most affected by water. Air will bring water in. Vapor is related to water. Thermal, you'll get condensation if you don't have enough thermal insulation. So those are the 4 things that we really focus on. So when we look at these designs and we compare what's happening or what's traditional, in terms of what we see in the industry, these are some of the things that we have to be careful about. So if you look at this design here, some of them have house wrap, some of them have tar paper. I have actually never seen tar paper do that, where there was enough water draining out and down the tar paper. It is an organic material, but it totally destroyed the tar paper. So these are constantly things that we run into in wood frame construction because we haven't addressed the window. If we had the window properly protected and that water was directed out and over the house wrap, over the tar paper, how often would we see this kind of damage? We just wouldn't see it. So that's where a big part of our issues are. Now, this is an example of a 4-side sealed window. So if you look at this, this is a 7-year-old apartment in Red Deer, Alberta. They've put blue skin all the way around, but the OSB is completely destroyed. Everything was draining into that opening, but nothing was allowed to drain out. So it completely destroyed an entire wall, 4-story apartment building, all the way up in behind there. Everywhere there was stone. So, you know, the rule of thumb in terms of balance is you want to let a certain amount of water in. It's fine if it gets wet, but you want to have an equal or greater amount of ability to get rid of that moisture or dry it out, because otherwise this is what happens. So this is kind of what got me into pushing for code change. Now, if you look at something like this one is open. This is a pretty typical construction you would see. Where's that water coming from? It's coming out from the rough opening. Why is it getting in there? Well, in this case, it was coming into the soffits. It was wind-driven rain. It was the exposure that was being experienced. The water was getting up into the soffits. It was running down behind the whole wall. And guess what you have in the sheathing? Joints. The water goes into the joint. Now it's on the inside. So even if you sealed the head of the window, the water's already on the inside of that opening. So the water ends up at the bottom on the sill. So how do you protect against that creating problems? So when we look at Division B, 927 of the building code, what we find is the building code is very prescriptive in Division B, and it says we have 2 planes of protection. We have the first plane of protection, which is your cladding, that's your windows, that's your glass. It's the sealant that connects the glass to the windows. All of that is first plane of protection. That's deflecting the water away, and it takes care of the majority of it. The second plane of protection the building code talks about is the membranes and the flashing, and it uses the term intercepts. So in other words, we know that our exterior claddings are not waterproof. Water's going to get through them. So when it gets through them, that second plane of protection, which is water resilient, is going to collect that water. Part of the second plane is the flashing, so when it hits the flashing, it kicks it back out over to the exterior. So it evacuates that. So it all comes down to how much water can get back there versus how much that can allow to escape. And that's where we run into problems with things like manufactured stone or stucco or materials like that, because we let more in than can get out. Vinyl siding, almost a perfect cladding because it lets tons of moisture out, lets tons of air blow through it, dries it out very quickly. So it really comes down to the safety factor in how we get water in and how we get water out. So those are the 2 main points that the building code talks about. Now, when it comes to windows, the building code actually defers a lot of our installation to the CSA A440 document. Now, that document has become so complex and so hard to understand, and at the same time, the 2019 version of it does not address the fact that we are letting water in and we need to drain it out over a sill-protected surface. It allows us to remove that and leave it out, except for doors and mold windows, and I don't know, when's the last time you saw a mold window, right? We just don't see those anymore. So when you look at the CSA 440, it talks about a lot to do with fastening and clearances and different things like that. But in 9.7 of the building code, it still says you have to look after moisture based on 927. And that's the moisture or the cladding section of the code. So it sends you back there, even though there's not a whole lot of information in 927 about windows. So it's very, very vague on what needs to be done. But what it does say, where it talks about second plane of protection, it says that the drainage needs to take that water and direct it back to the exterior by means of the flashing. So if you have a flashing there, the membrane needs to come over the flashing. There has to be enough space to drain it out. So I don't know about you, but when I see a stucco house and I see it stuccoed straight down onto the flashing and there's no drainage, that doesn't meet the building code intent of letting the water get back out. So Second plane is also a water-resistant material. We don't use the sheathing as second plane, and yet CSA says, hey, if you want to put that window in and you don't put any protection on the bottom, that's fine. So that doesn't really add up either. Second plane needs to be maintained at pipes and penetration, so it applies the same principle to pipes as it does to windows, which would lead somebody to believe that when you install a window, you have this flat surface of house wrap over the sheathing, and you seal all four sides of the flange to that flat surface because that's protection. When we know that's not true in reality, water gets into the rough opening. So that needs to be dealt with and brought out. So that was what precipitated the code change. So there's no explicit direction on how to deal with that water. Now, what the CSA does and what it doesn't do. First of all, it does a great job of recognizing water's going to get into the opening. We already know that. It does a great job of telling us how to structurally support the window, how to flash a window, how to detail a window. What it does not do is require a continuous membrane at the sill. At least it didn't in 2019. So 2007 version of CSA, if you're familiar with the document, 2007 we had this graph at the back, and we would calculate the exposure, and it was based on whether it was out in an open field or whether it was in the city, how tall it was, how big the overhangs were. Beautiful document, which in 2019 got taken out. And then in 2024, we added all that back in, but that never made it to the 25 code. So we said, wait a second, what's the two biggest things that happen when we install a window is the water gets in around the rough opening and it sits there and destroys the bottom sill. Well, we can fix that by putting a membrane in there, but what if I put the membrane in and then I spray foam four sides of that window? Does that limit the ability for the water to get back out again? So how do we address that? And what proof do we have if we choose a path and how to get there? Like, we can't just start doing things without having some proof or some background. So that's where we look at the building code existing, the CSA standard existing, and said, what does the industry do when they install windows? If you hire a building envelope consultant to come to your project, what's he going to ask you for? Well, he's going to look at the sheathing and go, okay, need to protect the sheathing. But then he's going to look at the rough opening and say, well, that's part of second plane of protection. It's going to get wet. How do we protect it? So he looks at that and he goes, okay, so where the sheathing goes, that needs to extend into that opening to protect the jambs and the head and the sill. Well, what do we do at the sill? Because we know that membranes typically are not waterproof. If you have any kind of static head, moisture sitting on there, it eventually works its way through. So we want something more robust at the base. So we put in there a seal of some sort. We put a liquid membrane, or we put a peel and stick. We put something that's going to resist water that's under pressure. So now, if water gets in there, it runs around the window, which is made of vinyl or wood. It just drops to the bottom, and it's protected until it can either evaporate or drain out. And then the cladding goes on, and we always remember to put the siding on and add caulking around there, right? So how much goes in, how much comes out? We have this moisture balance that we achieve, and we give it a way to dry out. So that's what the envelope engineers are telling us that's an important thing to do. So with the code change, there was two things that we looked at. One was the PCF that said, hey, right now in 927, it doesn't really give us any indication of where second plane of protection stops. It almost indicates it stops at the face of the window, at the sheathing. So we said, let's extend that so that it goes inward, and let's put a sill that's a mandatory water-resistant sill at the bottom so that whatever water gets in there hits that sill and is drained forward and safely back to the exterior. Because that not only protects the window, it protects the sill, it protects the cladding. We've been to buildings where you start taking the cladding off and there's absolutely nothing left of the sheathing, and now you're into structural deterioration. And some of these buildings are less than 10 years old. So when you get that extent of damage, that can be pretty disastrous. So that was the first one. But then we said, well, what if somebody chooses to put a membrane in there and then puts the window in and fills it full of spray foam? Does that cause a problem? Well, in the 24 version of the CSA standard, we addressed that and said, you need to use a drainable material at the base. So what's a drainable material when it comes to insulation? Well, you could use a fibrous material, but that's kind of a hygrophilic material where it absorbs the moisture and holds onto it. So we wanted something hygroscopic that, there we go, hydroscopic, yeah. Hygroscopic that doesn't allow it to absorb. So when it's phobic, it's fear of, it doesn't absorb. So a mineral wool or a stone wool will hold that moisture and drain it back outside. Plus, it gives you a lot better air tightness than a fibrous material. And a fibrous material, like a fiberglass, will just hold on to that moisture. And if it's sitting against a piece of wood, that's just going to eventually keep it wet for long enough that it's going to deteriorate and break down. So we looked at those two things. And what the code now says in 2025, it says you need to treat the rough opening as a second plane of protection and mandatory sill pan, no matter what you put in there. So that doesn't get adopted provincially for probably another year, year and a half. And if CHBA has their way, maybe it won't get adopted, but we'll see what happens with that. So that's coming in the future. But the other part of it was we said, what happens if you're doing high performance windows, you want to use a spray foam or another material, or maybe you're in a situation where that's the only material you can think of to use. Do you have to put insulation at the sill? And there's some studies that were done by NRC back in 2006 and then again in 2007 that studied the impact of not being able to drain that sill pan. And they said, is it the end of the world if you remove the insulation? And the answer was, it doesn't look like it. It looks like it still performs good. So the building code change was not to say, don't insulate. The building code change was to say, it's optional. And it goes into 936, which is the energy code, and it says, if your total insulation level, like it used to be, you had to have the same insulation value of what the minimum average of the window was. But now what they've said is you can remove the sill so that it's allowed to drain out. So that allows that to occur. But remember, just removing the insulation doesn't solve the problem. So what else do we need to look at as design features of the building? So if we go back to the basics, and this is some of the designs that we worked with CSA on. So CSA actually has a really nice website that has all the detailed drawings for flange window installation and non-flanged window installation. And they put those drawings on there. They're actually animated, so you can, send it to your renovator or your framer or somebody installing windows, and they can go through that and they can see exactly how it's done. These slides that I'm showing here were for the LEAP program. So LEAP, Natural Resources Canada, has a LEAP program, and that program has a whole section on specifically window installations, and so that's what this was coming from. But if you look at the main principles in moisture, we control moisture entry. We don't let too much in the first place. It doesn't say we stop it. So I always say, how often do your clothes get wet? You don't have to prevent your clothes from getting wet. If you spill water on them, how long does it take to dry out? As long as it can dry out. So the second part of that is moisture accumulation. So if you prevent moisture accumulation, now the wood isn't getting wetter and wetter, and the insulation's not getting wetter, and everything's starting to deteriorate. So you're controlling the entry, you're controlling the accumulation into the materials, but the third one that we need to do for this to be effective is we have to provide removal. We have to get rid of some of that moisture. So what do you do with clothes? If they're too wet, you throw them in the dryer, right? If you've got a hockey bag and you play hockey Friday night, and you zip up that vinyl hockey bag and come back next Saturday, how often is your hockey gear still wet from the week before, right? If it can't dry, I know that's a terrible visual, isn't it? Yeah. But that's part of the process. If you think of how moisture works, control the entry, control the accumulation, provide removal, if you can do that in whatever you're building, you will not have a problem. Things get wet. Things will accumulate a small amount of moisture, but it doesn't stay wet if you can remove that moisture and dry it out. So the other thing, if you look at that bullet point there, it says treat fenestrations as porous. If you treat them as porous, and that second plane of protection is just like the siding, where the siding is first plane, the water gets through, you're not expecting that sheathing at the backside to protect everything. You have another membrane there. Well, the windows are the same way. If you have a secondary layer in there, so that if the windows are porous, or 15 years after you installed them, they become porous, or there's something that happens that causes them to become porous, then that water is not going to make it to moisture-sensitive materials, and you're not going to have problems with the building. So that's an important aspect. Now, understanding first and second plane of protection, if you think of first plane of protection, cladding and sealants are really the definition of first plane of protection, but what about overhangs? What about decks? What about things that deflect water away from the surface? Anything that deflects could be considered part of this first plane of protection. But we know water's going to get through, so what's behind it? Well, we have a weather barrier and a flashing. What's the best weather barrier? Well, I don't know, whatever you can afford, depending on your environment and your climate. Maybe you want to go to a vapor-permeable peel and stick. Maybe you want to go to just straight tar paper. Maybe you want a house wrap. There's only 1,000 house wraps to choose from, so you've got all sorts of options depending on what you want to do. The goal is, though, that it deflects water, but it's vapor permeable enough that the moisture that's behind it can dry back to the exterior. It's kind of like wearing a cotton t-shirt in the summertime, right? Remember the old polyester shirts? I'm thinking back when I was in the 70s, right? In high school, those polyester shirts in the summertime, you just sweat like crazy in those, right? But a cotton shirt lets all that moisture out. Same principle with what we're talking about here. So again, second plane of protection, you got drainage. It includes the rough opening, includes the soffits. Wherever water's going to hit, that second plane of protection needs to be in place to bring that water back out. Now, I'm talking real fast because I'm trying to get through all the stuff that I want to talk about. But if you guys have any questions as we go through this, just fire them out, yell it out, whatever. Like if something's not making sense or you disagree, I love a good argument, so let's go for it. All right. So here's where the change is happening in the building code. And really, it's all about common sense. If water gets in there, there's just moisture-sensitive materials that need to be protected. So now that you've got this application where you've got that sill pan, even if you don't do the sides, you got gravity as your friend, right? Water gets in there, it dribbles down onto the top of the window. The window's made of vinyl. In most cases, it dribbles down the side of the window. It doesn't touch the wood. It hits the bottom, which is made of wood. If you don't have a protective coating on it, then it just sits there and soaks in. In the old days, you ever done a renovation on an old house? You pull out the old window and it's got tar paper in the rough opening and you lift the tar paper. What's the wood look like underneath? Pretty deteriorated, pretty rotted, right? And the difference between old and new buildings, what's the biggest difference in modern construction now versus houses we built 50 years ago? Like, this is a factor of everything. We have higher insulation levels, we have higher air tightness levels, and what are the two things we need to dry a building out? We need air and we need heat, right? That's what absorbs the moisture and holds it in suspense into the air instead of depositing it. So we build these modern houses and we put all this extra insulation in it, and we use the same construction method. That doesn't make sense. So we need to get rid of that moisture, but old buildings, you take them apart and they look like they're pretty good shape. I'll bet you if you added extra insulation to them and sealed them up the way we do a modern building, they wouldn't survive very long. So it's all about drying and get rid of the moisture. All right, so let's look at how a typical wall performs. So this is a water test. We used to do a ton of these all the time. And we're doing a water test. We put a blower door in the house to simulate a pressure differential. And then we would put water, we would tape the windows off because your windows never leak, right? But how do we know that? How do we prove that? Well, we tape it off and we test the wall, and then we pull the tape off and we test the window separately. Now, why is the water coming out of the middle of the stucco way over on the left side of this building? Partly capillary. But if the water comes, it gets in behind the window and it runs down, doesn't it also run a little bit sideways? Now, look at the head of the window. How does the water get out of that flashing? That flashing is supposed to take second plane of protection water and dump it outside, but you just sealed it. Now, the other thing about this, if you look at the video closely, I'm just going to back it up for a second. Look at this location right here. What do you notice happening underneath that window? It's draining, it's wet. Right? So in this particular application, this particular house, they had installed everything correctly. They'd put a sill pan in there. They were still getting a water leak. But the water leak was coming from the fact that the water at that window head couldn't escape and come back out. So now it builds up a hydraulic pressure. And what's your overlap on your house wrap? Or you wouldn't use house wrap here. On your tar paper, it's about 4 inches. So it builds up enough of a hydraulic head, it lifts the water up and over that joint, and now it's on the inside. And now it hits the floor joist, and now it's on the inside of the sheathing, and now it's running down the inside of the sheathing, hits the window inside, because they've sealed the window on 4 sides. Now on the inside, it hits the sill pan, and now it's draining out the way it's supposed to. So even though maybe 3 times a year this building will have water getting where it shouldn't, it's not going to suffer catastrophic failure in the long run. So it's an example of water getting through there. First plane is working properly. There's some sealant missing, and that's what we were able to discover doing the test, but it was performing the way it was supposed to. It was getting rid of the water the way it was supposed to. The other thing we look at when we look at buildings is during construction, people don't always look at a building and properly detail it in a manner that the guy coming behind them is going to pick up on that, right? So here's a condo building. You can see that they've pre-papered the walls. They have not pre-papered the gable ends. But they did put a peel and stick on the roof, which folded over to the face, which is nicely stapled on the face. So typically, what should happen here? The next guy coming along should continue that paper upwards. He should lift that peel and stick up and tuck his paper underneath it and pull it down. Well, how many times is, well, it's not my job. And it goes over, so now the water's on the inside. And because there's no overhangs, we can seriously increase the risk of water getting in there with no overhangs. Excuse me. So once the water's in there, now it's running down the wall and it finds a joint. So if that window on the upper section is completely sealed on the flange, 4 sides, that window will never leak. But what about the window on the next floor down? What about the floor joist space? The water that's running down the floor gets in behind the sheathing, and now it's dripping out the head of the window. So these are some of the challenges when we look at the design. It's not the window that's causing the problem. It's the water that's let in and getting into that location that's causing the problem. So a lot of times the window designs and the window detailing we do are to compensate for partially poor construction in other locations. So it's kind of like an insurance policy. It's protecting us from having that problem down the road. So that's the principles behind the building itself. That's first, second plane of protection. Now, how do we interface a window with that application? Well, if we look at it on a close scale, we've got a cross section of a wall here, so the outside is on the right. First plane of protection is your vinyl. Second plane of protection is whatever membrane, WRB, you want to put on there. It could be a house wrap, could be a tar paper, could be a peel and stick, vapor permeable peel and stick. In this case, we're showing a flanged window. So we've got a triple glazed window, but see where it says insulators? Right, so there's insulators here, these empty cavities in your vinyl windows which separate spaces. So if you're getting convective looping, it's not interconnecting to the next one and the next one and the next one. If you had just one big empty space, that convective looping would bring cold air right to the face of the window on the inside. But because they're each individual small ones, it's the same principle as an IGU, right? You've got the separation of the movement of the air in there, and so that exterior temperature is never the same on the inside. Even though you haven't filled that full of fiberglass insulation or some other insulation. Like, you can get windows that have those filled with foam, but how much of an improvement does it make? So that's my first question. Now, if you look at the interior versus the exterior and you look underneath the window, you'll notice we have, what we've drawn there is a backer rod and some caulking. And the purpose of the backer rod and caulking is to provide an air barrier. And what's the air barrier for? Well, it's to prevent the wind from moving through into the building. What happens when the wind is blowing, and the wind can blow from outside all the way into the interior? If it's minus 30, what's the temperature it's pulling in of the air it's pulling in? Warm or cold? It's going to be cold. What if it's raining? It's the summertime and the air is flowing from outside to inside and the rain is hitting there. Does it not pull that rain into the cavity as well? So that's the other problem with having that interconnected, is if we don't have a good air barrier there. I illustrate it sometimes using a water bottle. Like, if I take this water bottle and I pull the lid off the water bottle and I turn it sideways, if this is the outside of the flange, I got about a 3/4 of an inch hole there, right? If I take the lid off and poured the water out and tried to blow air in here, how much air could I blow in there? Lots? Little? Almost nothing? Right? It's going to pressurize the cavity. Now, if I take a pen and I poke holes in here, as I blow air, it's going to flow through. And what's interesting is, if you do this at home and you poke holes in there and you blow air through, this bottle will completely fog up. If there's no holes here, it doesn't fog up at all. But what it illustrates is that the air is the transport mechanism for the vapor, for the water, the liquid, for the cold air, whatever is there that's getting transported into that cavity. So if you look at the outside of this window, the outside is not necessarily sealed. The inside is sealed. The pressure plane is on the inside face. So now if water gets in there, it doesn't have any reason to continue on and go inside the building. It doesn't have any energy to continue on and go inside the building because that cavity is completely full. But let's look at how it deals with water. So initially you have first plane of protection and the water comes down the window. It comes across the window, and right there we're missing a little bead of caulking. So if the air could pull it in, then it might get a little bit of water into that rough opening, but it's wide open so that the water can drain through. So the water is being deflected away. The flashing is doing its job and kicking the water away. Then we also have a secondary drainage in the window itself. So a lot of people don't realize that windows need to drain excess water that gets in there. Sliders and casements, not so much pictures, but a lot of windows have to have this internal drainage system so whatever water gets in there can safely leave and drain back outside. Well, that same principle is what we need to apply to the rough opening, because the rough opening is going to get some water in there from some source. Is it able to freely get rid of it? So that incidental water that gets in there, because even if it's just a little bit of moisture and it gets a little bit damp, and then a week later it gets a little bit damp, and a week later it gets a little bit damp, right? You're starting to accumulate the moisture level, and what starts to happen to the ability of that wood to grow things or to mold, right? That just goes way up. So those are the conditions that we're looking at here. So there's the planes of protection that we're talking about, and there's how the rough opening interacts with that face. Now here's another window. This is a non-flange window, and I'm not showing the shims, but there's shims there supporting the glazing and the glass, but we're not showing that. It just makes it a little bit easier. But you can see the same principle in how this is designed, is that the water on the face is draining away because there's no ability for air to flow through, and if the air can't flow through, it can't carry anything else with it. It can't cool those inside surfaces. It can't bring water in, so that protects that. And you still have that internal drainage that you had with the flange window. And then you also have the ability to get rid of water that gets into the rough opening. So those are the basic principles. And every window is slightly different. Some are, more finely tuned to have more cavities, more spaces. Spaces are smaller if you want to spend more money on them. Some of them are insulated. But when it comes back to this question about the 3/8 gap in installation, what do you see wrong with those two middle pictures? Like, this is probably going up to about 10 years ago. And in fact, if I drive out to Ottawa and drive around in Ottawa, this is typically probably what I'll see. Instead of tar paper, I'll see house wrap, right? No protection really whatsoever when it comes to the rough opening. So we're installing these big windows. We're spending a fortune on windows. The window isn't going to be affected by the moisture. Like, vinyl doesn't rot, but the wood wall will. So the deterioration is in the actual structure. So that's where the risk is all being handled. So let's think about compartmentalization and sealing. I said, if I try to blow air in here, I can't do that. I can blow all day long, but until I poke some holes in it, I'm not going to be able to do that. And even if I blow some holes in here, some fairly large holes, I can still create a pressure in the window. So if we think of compartmentalization and you think of a car door or a car trunk, what do you notice about when you're closed all the doors and windows on your car and you're driving down the highway? Does water come pouring in if it's raining? Like, why don't we seal the outside? We could call that the flange on the outside of the window. Why don't we seal the outside of that door? Because as we're booting down the highway, the wind gets pushed into that cavity, creates a high pressure space behind there. If the pressure is high, how much water goes into that joint? Almost nothing. So if the water's not getting into that joint, how much pressure is on that weather stripping to keep water out of my car? It's very low. So that principle alone teaches us that compartmentalization or partial compartmentalization keeps the water from flowing into those cavities, which is what we want to look at when we look at a window. We just want to think about, how do I reduce the volume of water getting in there? And that's what rain screen principles are based on. It's not pressure equalization as much as it pressure moderation. Equalization is very difficult to do, very challenging. But moderation, you just need a higher pressure on one side than the other, and it performs really well. So there's the principle behind the rough opening. Now, if we convert that principle to a window again, and we look at the green dotted line, here's our pressure plane. And if you think of the pressure plane, so it goes from the inside of the glass, around the inside of the frame, down through where the caulking and the closed sill backer rod are, and then it could flow straight down through the 2x4. It doesn't matter, anywhere in that bottom 2x6 material is all going to be the same air tightness. And then we carry it back in and we carry it to the inner air barrier, the poly that we put on the inside. Now, where would the weak connection be in that application? Well, if we didn't seal that, or if we didn't seal it or put a compression on that, it could create some ability to air to go through. But if we maintain that nice airtight seal and the water that gets in there has no reason to stay, it just drains back out again. And that's the principle of curtain wall systems. When you look at high, tall buildings, when you think of a curtain wall, it treats the glass or the glazing as porous. The water gets in and around it and it just drains it back out. Like, how could you resist 400, 700, 1,500 pascals of pressure on a tall building unless you did that? You can't seal it up perfectly enough. So it's oftentimes very difficult to seal it. And then we compare the air barrier. This is a very common situation we used to run into throughout my career in terms of people complaining about air leakage on the windows. Because in some of the western provinces, we buy the window with the jam extension already connected to it. So it gets shipped to site with a jam extension connected to it, and then we install it, but there's no air seal between the jam extension and the window, and you're relying on the insulator, who probably a week ago was working the till at Tim Hortons, and now he's a professional air barrier installer, right? Not his fault. He just doesn't understand the principles that are needed to make sure that this doesn't leak. So he comes out with a foam gun, just like his boss told him, and he spray foams all the way around there, but he didn't make it to that joint where the window connects to the jam extension. So now think of the consequences of this. If it's minus 30 outside, and that's the windward side of the house, as the wind is blowing in, if it blows right through that assembly and then out the back door through the other assembly in the back door, what do you think the temperature of the casing and the inside of that jam is going to be? Hot or cold? It's going to be really, really cold, right? Even though there's spray foam in there, even though everybody said, well, I did my job, I put this in, but it's just not done well enough to stop that. So we get that flow. What about in the summertime? If the rain is beating down on the face of that window and the wind is blowing, it's just going to pull all that water right into the building. So it's not just about condensation at that cavity. It's not just about stopping the air at the cavity. It's the consequences if we don't stop the air at the cavity. So that's why that's important to think about. Some people talk about spray foam as being a great insulator, but also can work as a great way to, let me just get this rolling here, as a great way to keep water from coming in. Because the concept is, if the water doesn't come in, question? Yep. Right. So if you think of the cross-section of the window, so the question is, how do you know that the water that's coming in isn't just going to bypass everything, all that air barrier you put in there? If you think of the cross-section of the wall, where could the water possibly come from? So it could come in the middle of the wall, but how does it get there, right? So it's going to come down the inside of the sheathing, it's going to come down on the outside. If the window fails, where does the water come? Like, let's say you move a window around in the middle of December and it's minus 25 and you break something inside the window and you install it and you don't see it, and just, expansion, contraction over the course of the next year, it opens up and water starts leaking out. So you want that air barrier, that plane, to be inboard of the inside face of the upper part of the window, right? You don't care about the jam extension. You just want it inboard of that connection. Yep. Yep. Well, yeah, well, it is possible. It is possible, but how would it get there, I guess, is the question. So if you look at the design in that cross-section, let's back it up for a second here. Let's look at this detail here. So see where I'm showing the closed backer rod in the caulking. If water comes in from the inside of that, that's absolutely possible, but how would it get there, I guess, is my question. Because you've sealed it four sides. So if the water's getting in and get in. Right. Right. Well, no, because this is on the inside. This is 2 inches in from the sheathing. Even at the top, it's 2 inches in from the sheathing at the top. It's all the way around four sides. Yeah. And whether you use backer rod, whether you use spray foam and just control and don't fill the whole cavity, right? It's not that you can't insulate the cavity. It's don't insulate it so full that the water that gets in there can't move its way around and drain back outside. So hold that thought for a second. I think I have a detail that will explain that a little better. And rather than jumping ahead, I'll get you to hold on to that thought for a second. But you're right. If it comes from another source, then we need to move that air barrier line into where the lowest risk is. Because if we don't, we haven't really detailed it the way we want to. All right. So let's go back and talk about spray foam. Is spray foam water resistant? So when you look at most spray foams, they can be water resistant depending on them. Like closed cell medium density spray foams are water resistant. A lot of the newer window foams form a skin on them so that they become water resistant. They don't soak up water. They're hydrophobic. They resist that water. But if you cut the skin, does that still occur? In other words, you do all the things you're supposed to do correctly, and that foam's hanging out 1/4 of an inch, and the finishing carpenter comes along, and he can't deal with that, so he cuts that face off and trims the window out. Is that going to soak up some of that moisture, right? So those are the risks that we look at when we look at all materials that we're looking at in the building. So this comes back to that question we started off with at the beginning, the 3/8 inch question. Is it sill protection and subsill drainage? How are we dealing with that? Insulation and the subsill rough opening, how are we dealing with that? And then how important is air tightness? So rather than looking at the building science now and what everybody says is going to happen, let's look at what the testing shows is going to happen. So there was a series of tests that NRC did, National Research Council, back in the early 2000s. So 2006, one of the major ones Michael Lacasse was involved with was looking at performance of window details in driving rain. So why driving rain? Well, if anybody's had a window leak and tried to go find it, usually a builder will show up with a garden hose and he'll spray water at it for an hour and he'll go, see, window doesn't leak. But there's no pressure differential. You need a pressure differential. That's what wind-driven rain is. It's a high pressure on one side and a low pressure on the other side. You also need to know, is it the window that's failing or is it the installation of the window that's failing? So you need to separate those two when you're testing them. But if you look at this test, what they did is they took windows and put them into openings and they tried all sorts of different things. They tried sealing them on the outside, they sealed them on the inside, sealed them on both sides. They tried different types of sealants. They tried different insulations in the rough openings. They tried 25 different design tests to come up with their conclusion. And their conclusion was, water will get into the rough opening, you need a sill pan. That was the whole test in a nutshell. And that was the basis of what they were doing. So then, in 2009, they talked about it at a conference, and then they published a document in 2012. Well, that just raised all kinds of questions about what happens now if I put that sill pan in and then I spray foam 4 sides of the window, because what's the most common thing we use? It's spray foam. Well, if I spray foam 4 sides of the window and I fill that cavity the majority of the way full, how do I get the water out that could get in there? There's no guarantee that water's going to get in there. This is not, don't use spray foam because it'll get leaky, and don't, not put a sill pan in, because sill pans have been around for, the last 25 years. They've been in commercial forever, but in residential, we haven't seen them a lot, but we also haven't seen the level of insulation and air tightness that we're seeing nowadays. So that's the downside of that. So we're trying to change the way we look at it and say, well, if we can't dry it out, we need to do something to keep it from getting wet in the first place. So they did all these studies. So for their design with window interface details, window condensation potential, they look at the window design and they said, if we don't insulate the sill, what happens to the temperature on a minus 30-degree day? So what would you guess between, and we're not talking any wind, so this is not wind related, this is just what would happen with convection only, right? So you got a dead air cavity with no insulation. You have another one that they filled with fiberglass, and you have a third one that they filled with spray foam. So between the one with no insulation to the one with fiberglass, what do you think the temperature difference on the inside of the frame would be? A couple of degrees? What's that? Less than that? How about half a degree? Their instrumentation wasn't accurate enough to test it, but they came up with half a degree. When they moved to spray foam, the temperature difference was 1.5 degrees. So the temperature difference on the inside face wasn't affected by not insulating the sill, as long as you had a good air barrier on the interior face of the frame, and on the exterior you sealed the sides, the head, and the other side. The type of insulation was almost irrelevant to the interior temperature. So that was what the testing, so they continued to take the data and the information and produce additional documentation because they'd tested so many things and had so much information to write about. So, they talked about water entry and drainage, condensation, drainage, design guidance. They had one on condensation risk qualified, like what to do and what not to do, air leakage and pressure control. Like they talked about this repeatedly from all the studies that they'd done in 2006. So from that study, what they found is when you look at the initial study, those things that we talked about, the sill pan protection and the overall performance, the only way that you could assure not having a leak was to pretend the window or the door was porous and build in the sill pan to pick up the water to make sure it disappeared, right? It didn't get into the wall assembly. Tested 25 different figures or different installation configurations, controlled deficiencies. That's the other thing they did. They put little imperfections in. They broke the flange. They put spacers in the flange. They did all sorts of things to measure what was the worst case scenario if guys were not really paying attention when they installed these on site. And they were able to identify some things that made things change. Wind-driven load pressures. They measured air leakage. They compared different results and strategies. You know, they looked at sealed versus vented flanges, all sorts of different things. And then in the condensation one, this is where they got into the temperature differentials. They controlled the air leakage rate, like how much. They also put pressure differentials. So not only did they test them with no wind, they also induced pressure differentials of 20 pascals and 40 pascals. And the result was, again, almost no change in the temperature on the inside face of the frame. They were able to get really cold temperatures in the cavity itself, but that didn't affect the frame temperature. So the question was, if we don't insulate the bottom, what happens to the temperature of the inside? Is it cold enough to contribute to condensation? And for the most part, that's not the case. It doesn't really work that way. So that was an interesting conclusion that they came up with. This is some of the quotes from the documents that they had. Water accumulated at the sills must be drained. Condensation was assessed as a function of both temperature differential and air leakage across the test assembly. Like they came up with some really strong opinions on, you know, whether we should put a good air seal in the building. And at the end of the day, that was the most important thing, is having a good interior air seal where the window connects to the wall interface. And that was the most beneficial thing they learned in this whole study. So when we apply the building science, and we look at the building science and what this is telling us, it's telling us that when we look at a window, for instance, a PVC window at 0.16 to 0.19 watts per meter per Kelvin, or Celsius, depending on, you know, what you work in. But if you look at the temperature difference between that and wood, very similar. So even though the test was done on vinyl windows, the wood has got a very similar thermal conductivity. So when you think of the materials and the wind or the air in the house reaching those materials, it doesn't take much to hold the temperature warm to reduce the condensation, as long as you don't have air leakage influencing the surface temperature. So whether that's a flanged window or whether that's a non-flanged window, again, when you look at the non-flanged window, it looks like there's tons of room for air to blow in there. But again, remember the compartmentalization aspect of that. It's never going to be perfectly airtight, but if it's 80 or 90%, you've still got that moderated pressure differential between inside and outside. So the code change that was talked about is to provide drainage and sill protection. So it accomplishes that effectively. And done like this, you can do all sorts of fancy things with that sill protection. The code isn't saying that. You know, you need to assess your environment and the amount of wind that you're facing and how tall the building is and all those other things to determine whether you need a back dam and how robust the back dam needs to be and how well it needs to be sealed. Those are all addressed in the 24 CSA standard. But from a basic minimum standard, it's saying if water gets in there, protect that sill long enough that you can get rid of that water and it doesn't damage the surface. And that applies to flanged or non-flanged windows. So, having said all that, builders still continue to argue that if I don't insulate the window, I will get condensation. That's my biggest concern. So rather than just say, don't worry about it, why don't we talk about what causes condensation in the first place? Like, why is that pop can wet? It's probably cold, but what's in the air? Moisture. So if you have moisture in the air, if you take a pop can today in this room, if this was really cold, just took it out of the fridge, I'll bet you I don't get a whole lot of condensation on this. It's pretty dry in this room, isn't it? But if you had this outside in the backyard and it's 80% humidity, this thing's going to sweat like crazy. So how much moisture is in the air? So that's a factor, and whether it can hold on to it. What about the frost on the glass there? Did we used to have mullions that actually touched the glass inside? It's just bridging right straight through, right? So different spacing on the glass, different materials, the frost and the ice at the bottom. So we understand what condensation is for the most part, right? It occurs on cold surfaces, it holds moisture, and what happens is at that cold surface, at the edge of the cold surface, you have this, if it's not moving, you have this boundary layer of air. So if you do an energy calculation, you have a boundary layer of air on the inside of the wall, and you have a boundary layer on the outside of the wall. And if there's no air movement, that boundary layer just sits there, stagnant. Well, what happens if that boundary layer is against a cold piece of glass? The temperature goes down, what happens to the relative humidity? As it cools, that air shrinks. Can't hold the moisture, so the humidity goes up. You ever take a water bottle and throw it in the freezer and go get it in the morning? Leave it in your truck overnight, a -20 night, right? It just shrinks up to nothing, right? The air shrinks, can't hold the moisture. So now you have this piece of glass that's cold because it's -20, -30 outside, and the temperature's cold, and that boundary layer is not moving because the drapes are closed and the blinds are down and the furnace is off, there's no air movement whatsoever, so now it starts to sweat on that surface. So that's where you have to get into and look at, what type of window should you use, right? You could use a double glaze window. You could use a triple glaze window. You could use a double that's an average. You could use a double that's the best. Where's the coldest spot on that whole window, though? Where do you start to see the sweating or the frost on the window? The frame edge, the spacer bar. What about the frame? Look at the temperature difference from the frame. Center of glass is one number. Frame is another number, but look at edge of glass difference. So that's where you're going to start to see the buildup. So the argument that removing the insulation in the rough opening doesn't hold true to the science of where the temperature differences are on an actual window. Plus, if you look at the ability of that window to absorb heat, that thermal conductivity, it'll warm up really fast just by showering a little bit of air over it. So if I do that, and I look at that boundary layer of air, and I say, okay, well, maybe I put that style of window in. Like how many styles of windows are there on the market, right? You could use a style of window like that where you have a little extra spaces on the inside. Look at the spacing on the inside versus the outside. If you think of insulation in the wall, and you think about where the wall sheathing is, don't you try and put more insulation outboard than you do inboard if you want to reduce your problems with the sheathing getting wet? So look at the amount of plastic on the outside of that glazing point to the inside of that glazing point, right? That window is going to be much warmer than if you split that 50-50, or if you have all your empty spaces on the exterior and hardly any on the interior. So the design of the window could make a big difference too. So when you look at the windows, it's that boundary layer effect that affects how they perform. So if you get to the 0 point, it'll condense. If you get below the 0 point, it goes straight to frost. You get a phase change either from a liquid to a gas or a liquid to a solid. So that's the difference when we're talking about windows. So if I did a quick math calculation, assuming that that window was 5 feet wide, and I had a buildup of 1/2 inch by 1/2 inch frost on that window, taking the volume, that converts to a mass of 0.23 kilograms. If I take the energy required now to get rid of that ice on the window, I need enough energy and airflow to melt the ice, but then I also need enough to condense or to evaporate that moisture back into the air. So I need 650 kilojoules of energy to do that. So if I look at standard airflow, how much is in the air? If I put 25 CFM of air towards that window, I get about 230 watts of heat. If I put 50 CFM, I get double. 100 CFM, I get double again. Like it's just the amount of energy that's in the air to melt that and evaporate the moisture off of there. It's no different than taking a hairdryer and drying your hair. I remember those days. Anyway, so you look at frost here, and we convert that. We say, okay, we need 650 kilojoules, which is equal to 650,000 watt seconds, and I can figure out how long it's going to take. With 50 CFM of house air at about 25% efficacy, it's going to take an hour and a half just to get that window back to where I started it. If it's 100 CFM, it takes half that amount of time, but if you've got frost or condensation on the window, you're already behind the 8 ball. You need the air flowing over that before you ever get started. Otherwise, you're way behind the 8 ball. So now go back to this one and say, how do I keep that from happening in the first place? And then think of the science and the testing that says the glazing, the glass edge where the spacer is the coldest point. I might not be able to stop moisture there, but I shouldn't have moisture on the frame. And when I look at the detail here and say, all I need to do, like, go down to that 25 CFM and get a multi-stage furnace instead of a single stage and turn it on to a really low volume so the air is just barely moving in the house. And let's say I'm putting 5 or 10 CFM on that window. 5 CFM would give me 46 watts. That's more than enough to keep that vinyl window or a wood window from getting any kind of condensation or moisture on it. Like there's enough math. We know how this is working. So what was the results of the testing from NRC? At the end of the day, at minus 30 outside, with no pressure differential, the temperature remained very similar. 4 to 5 degrees between high and low, and the insulation made no difference. Once you got air pressure differences, it made a big difference in the cavity, the rough opening, because with fibrous insulation, the air that leaked into the rough opening could push through the fiberglass and spread the cold. Couldn't do that with the foam, so that foam helped reduce the air leakage, but it wasn't anything to do with the insulation. It was everything to do with the air leakage and the pressure differential. And when you talked about 20 to 40 pascals, that's a huge pressure difference. You would never experience that in your house unless you hire somebody to come and do a blower door test on it, right? Those are big numbers. So typically, you're not going to experience that. So what it tells us is that when you look at these different materials in terms of insulation or no insulation, yes, I'd always prefer and go on the side of insulate the rough opening. But if I take the steps to, first of all, install the window, seal the outside 3 sides, let the bottom open, drain out, because I put a sill pan in and I let that water escape. Then on the inside, I give it a 4-side, really good airtight seal. And that way I can accomplish this. So that's kind of what we need to look at in terms of what's the conclusion to the testing and the results. It's really that, we want to look at the airtightness of the window and the rough opening. So that is my presentation in a nutshell. I'm going to jump back to that one slide that I promised I would show you here. Let me just find it in my slides. Maybe I ended up not using it, but I do have one here. Here it is. Ooh, squished. So your question about where do you seal it? Well, it didn't show it.
So in the meantime, Daryl,
Yep.
if I can ask a question, because ask 2 questions. One is complementative to the first. Why add insulation to the rough opening cavity at all if the research that came back from it said that it was essentially ineffective on the temperature, and from what I remember reading from it, it also increased the risk of water retention? So if you have exactly what you're talking about with the spray foam and you've cut the outside face, they're acting as little straws that are essentially holding on to the water, and then you got that up against potentially a air barrier, not something non-permeable. So why? Why would you lean on the safe route which a question of adding insulation to the rough opening cavity.
Why would I do it? Because I want to sleep at night. And something in the back of my mind says, you can't leave that uninsulated. So I'm not arguing against not insulating it, but look at it this way. If I put the sill pan on there and I reduce the air pressure ability by getting a good air seal, you're right, no issues. I'd still throw mineral wool in there.
Okay, so that
That's
leads
just the way
to,
I am, right?
it leads to the complementative question, which is, do we need to go back and redo that testing from Lacasse? Like, is it time for us to come back to that research and validate it? Because I think there was plans at the time to actually do a round 2 of that. And
I can think of 20 different things I would test to redo, not to redo what they did,
Yep.
but to simulate what's best and worst case scenarios, just to get another layer of verification that, that's actually what's going to happen.
So if we had, a heat box lab and the ability to do that testing and say a university that was thrilled to do it with us, would you be interested to help us shape some of what that looks like?
I'd love to.
Okay.
That's the fun part of the whole job.
All right, be careful what you, no good deed unpunished.
Come on out to the West Coast.
There you go.
Which one would you like?
Okay. Let's see. There was, it's at the very end of the presentation, a few pictures after in my leftover materials. One more, keep going. You're going to see a cross section coming up right there, that one. There we go. Okay. So when I look at where the plane of the air tightness is going to be, I look at that whole rough opening and say, where is the last point water's going to get in there? And I always start at the top. So if you look at the top right, you see the floor joist. So that could be the upper floor. It could be a flat roof, low slope roof. See where the sheathing is open there, where I've got that little red line at the top? So if water gets in above that, it's running down the sheathing for whatever reason it got there. It gets to that point. Now it's inside the sheathing and it's running downwards. It could, see where the arrow's showing? It could run down in between the sheathing and come in, but it also could be hit by the 2x10s and come in the 2x10 and run all the way inside and down. You're absolutely right. But the risk, from my experience, is lower than where we're saying to do it. So you're absolutely right. Like, if you're concerned, I would just air seal the whole thing, do it at the face. Because depending on your jam extension too, like if you're buying windows with a built-in jam extension and you air seal that jam extension when you install it, put the air tightness at the face of that where it meets the casing, you've covered it all, right? So as long as the material that's in there can support whatever moisture gets in, it drains it out, Bob's your uncle. Does that make sense? Did that answer your question? Yep, go ahead.
Does it make sense to, in modern building code with really deep walls, like the extra insulated walls, to move the glass plane further inside than we typically do in construction? So
Yep.
that we have the air movement past the actual glass?
Yeah.
Rather than a deep cavity where it's hard to get the air to flow into?
Exactly. So have you built any net zero or passive house buildings?
I bought one.
Okay. So what do you buy off the shelf to finish from the face of the window to the outside of that ledge when you set the window in? You have to custom make something. I think that's the biggest risk. Like any of the net zero stuff in the passive house we've done, we couldn't find an off-the-shelf product. There is a couple of window manufacturers that have attachments that can be fastened to the front of the window, but generally they're not big enough in that application. So if you're doing a double wall system, say where you got a 2x6 and a space and a 2x4, if the window is inboard, closer to the interior.
I'm more on the research you were talking about the air movement past the windows to keep the condensation off the face,
Oh,
like
that
the
was
dead air
just,
barrier.
we haven't even tested that. It's just a calculation based on physics, right? How much energy does it take to absorb and deal with moisture? How much energy does it take to keep a piece of vinyl warm if we know the thermal conductivity? So it's not saying it'll be perfectly dry all the time. We just have the ability for air to flow in and around it. So I built a house about 10 years ago, and it's got triple glazed windows. And they're just basic vinyl windows. And in minus 30 day, if I take a thermal camera and I point it at the edge of glass where the spacer is, I'm sitting around minus 17 on a minus 30 day. Way below the dew point. But my furnace is running on a low speed, so the air is constantly, that boundary layer, if the boundary layer gets stagnant, it cools, condenses, and either freezes at minus 17, or if it's minus, minus 1 or 2, it might stay above freezing, or
But like on like a passive house where it's a really deep sill,
right.
are we seeing like a dead pocket?
It really comes down to whether that boundary layer of air is influenced, because your windows, I mean, what's the best window you can buy in the market right now? Like an average R8, R9 maybe? So is the air, like in the middle of your house, if you're operating your house at code conditions, 21 degrees, 35% humidity, that has tons of ability to absorb that moisture. So first of all, that air moving towards that location can absorb whatever moisture is there, but the more important thing is it displaces the air that's out there and pushes it out of the way. So depending on your mechanical system, depending on how it operates, we've done houses where we've put little grills that come up through that interior double wall, had little grills there that would shower the window with air. Because, well, they wanted energy efficient house, but they also wanted 17-foot aluminum windows, so didn't really.
Worst thing you can do on a really cold day is close your drapes and your
Yes,
blinds.
absolutely.
Yeah.
Yep. Yep.
Yeah, does this, right here?
Okay.
Oh,
Here we go.
Hey, does this change anything about what the siding guys and girls do? Like, do we always expect water to drain between the plastic barrier and the siding, like in between there, and then out the bottom?
It's usually going to come out your weather barrier, right? So it'll come out at the bottom of the flashing.
Is there any siding that doesn't work with?
Nope.
It's always been that way?
Unless you do a face sealed system. So if you're doing EIFS, EIFS used to be problematic, but EIFS nowadays has the built-in drainage, right? You have the geometrically carved out EPS foam that goes up against the vertical grooved adhesive that goes on there, but I can't think of any cladding that you wouldn't have drainage behind it.
Nice.
Yeah, no problem.
Hey man, what about doors?
Doors.
And the sill.
Well, you know what? We could spend another hour talking about that, but it's the same principle. It's the same principle. Well, they do, but the CSA now requires them to have space in 3/8 of an inch. On doors? Yeah, that came in 2019. It just, I've never seen it done.
No.
How many rotten sills have you seen?
Yeah.
With NAFs and having better doors, like doors have always been problematic. The other one that's problematic is outswing doors on decks, right? Because the deadbolts, the openings, everything gets in there, and then guys will put their decking on after the fact, and then everything drains behind the deck, right? That's problematic. But I think there's got to be a balance there. Like, I don't see the need to have the space underneath. Like, on the committee, I fought against that because I don't see the point of it. Like, what's the purpose of the space at the bottom anyway? For insulation. What's that? Well, that's always been my question too. Why do we put the flanges on the outside and not the inside so we can install them standing on the floor?
If you've got strap anchor windows, you could.
And now you got a better air seal on the inside, better chance of getting it, but we don't have any detailed materials for the outside. Like, because I do so many installations, I would completely change the design of the window. So.
Is there a resource for doors to show the same kind of detail?
Yes. Actually, if you, okay, yeah, just send me a note. But if anybody wants the detail from CSA, how do we get them out? How do I get it out to them? They want to contact you or Adrian?
Yeah, you could.
Okay,
Yeah.
I'll give you the exact link, because if you go to the CSA website, you'll chase your tail half the day finding it. Once you find it, it's real easy to get back to, but if you're looking for it for the first time, it's in resources like training and education resources. Yeah, so. Am I done?
No, you got another one.
Not yet.
I got another one? Okay.
Just a quick question. We've seen in some cold winter, and just this has only happened a handful of times, where we'll go out and people will have a frost pocket on their PVC jam.
Yep.
Now, from what you said, with no insulation to insulation, it should only be a difference of 1.5, half a degree.
Yep.
So inevitably, you'll pull the casing and find out there's a void in the insulation.
Yep.
There's no condensation, no frost in the window, anything. It's just there.
Yep.
You fill it up, it goes away.
Okay.
How does that work?
So is it thermal or is it air leakage that you fixed with insulation?
I don't know.
Yeah.
But I'm just saying, though, that
You're right, though.
yeah. How does that? If it should only be a half a degree or 1.5, either the whole thing should be frosting up, or it shouldn't matter if there was a pocket or not.
But if you remove the casing and there's a void there,
Yeah.
that's going to be an obvious air penetration as well.
Yeah.
So it's probably coming from air movement, bringing that cold through.
That would be my guess. The way I would diagnose that, I'd put a blower door in there. Well, first of all, I'd infrared it before. I'd put a blower door and see the difference in temperature, and then I would measure, if there was actual airflow through there. But I would guess, it could be a number of things. It could be a metal location, metal pieces in there. It could be, there's a number of things. It could be the homeowner, closing the curtains, and then when you get there, they open the curtains, and the only frost left is that, right, who knows? But, yeah. But there's always an explanation. It just takes a lot of work to find out what it is.
Right, yes, correct.
Yeah.
True.
Yeah.
True. I always ask people, okay, so you're going to walk from here. What's the closest mall from here? Who's in Winnipeg? Okay, so let's say you're walking 2 miles. You're going to walk 2 miles somewhere, and it's -30 outside, and it is windy. You're not doing that. Yeah. Well, you're probably not. But I'll give you the option. I'll give you a windbreaker, or I'll give you a heavy knit sweater. You can't have both, but you could have one or the other. Which one's going to keep you alive until you get there?
Yellow cab.
Yeah. Yeah. The air barrier will stop the suction of the heat away from you better than the heavy sweater. So air barrier is, to me, trumps thermal. So anyway.
Maybe just a question related to the difference, maybe playing devil's advocate from the 4-sided seal to the 3-sided seal. You're sort of advocating for the 3-sided seal, but aren't we just sort of moving the issue down the line? If we're seeing failures to the 4-sided seal relative to the air barrier, we're sort of pushing that problem in, allowing the window to potentially absorb some of that as a rain screen, but that plane of air barrier, you're sort of pushing to the interior, you're still relying on it as a sort of single source to stop. You're relying on the compartmentalization, so air can't get through, you're saying, similar to that sort of blowing through the bottle. But if you've got that, Tim Hortons guy next day working on and caulking that interior frame to provide that air seal, that's sort of that same idea of a defense as the 4-sided seal. But to me, you're just sort of pushing it to the interior. So, yeah, I'm just sort of reluctant to sort of say one or the other is better. There's differences there, but we're still having those issues of reliance on that sort of one, knowing the failure point as being that the air seal.
Yep. And I agree with you. Like it's about the quality of the workmanship. But if you were to do a couple of things, first of all, if you look at the installation and you think about if you don't get the air seal on the inside and the wind blows through, okay, so what's that going to create in the cavity? Moisture. Moisture falls on the bottom, it drains out. Has it hurt the structure? It hasn't really damaged the structure in that application, right? So if you didn't get the air barrier right, you might get some frost on the inside of that frame, and what's the frame made of? It's made of plastic. So I think in terms of moisture sensitivity, and I think in terms of damage, because when I go to a building that they've sealed 4 sides and it's got $1 million worth of damage on it, I think if they'd have put sill pans in and done some reasonable sealing, there would be probably $100,000, $200,000 damage. But in terms of priorities, or you could think of it, you know, take the weather stripping out of your car door and get somebody to tape you in and tell me if that works better in the long run, right? It's just a mindset of thinking, what is the best option? Like, there's probably way better options.
Right. I guess there's always those offsets where you're getting the benefit of that rain screen principle. You're getting water. You're presuming failure. At one point, you're getting water to shed out if it gets in. But then the offset of that is, are you then allowing air? Like for Winnipeg especially, we have cold climate, very cold air. You're allowing that air and cold weather to essentially get closer to. Now you have that cold air coming into the back of the window. Allowing potentially, condensation to occur rather than it sort of being, you're allowing that cold plenum to be further into and past the insulation. So it's sort of, you're benefiting one area where you're allowing that water to shed in the summer months, but at the same time, you're creating another vulnerability. So
Right. So are you thinking 4-side seal is a better approach?
it's just another approach. Like there's anytime you get into a new technology, there's going to be, you're in the Wild West where there's going to be problems you have to solve. So.
Yeah.
There are issues with that, of course, that you're trying to overcome. I feel like 3-sided seal might be a bit of a admitting defeat to failure. It might work in residential where, of course, you've got Wild West installations, but say commercial where you have outbound insulation and a lot more stringent requirements to kind of keep that out, where your AVB is sort of one plenum with exterior outbound insulation, then potentially there's some benefits there.
Right. So how do you explain a curtain wall working then?
So yeah, you still have like air and moisture getting to the air and vapor barrier plenum past the insulation, and that becomes your curtain wall principle. That's your plenum.
Right. I think that's what we're trying to do with the windows, is we're trying to take that principle of pressure moderation and just reduce the flow. And if we reduce the flow and water gets in there, we're kicking it back out. That's all we're doing.
Yeah, so like for sure I see benefits to 2. It's just, there's always the application, whether you're in the West Coast,
For
central,
sure.
cold, or even installation capabilities. There's sort of those benefits to both. Just playing devil's advocate, sort of pushing the element if you're selling one versus the other. But
Absolutely.
It's good to kind of see those two
You could ignore
perspectives.
both of those and set up your mechanical systems to pressurize the building so that you never have air coming in. You could pressurize it so that it's pushing out, just like a commercial building, right? So you can take advantage. Like, we're only talking about one dimension here, where we have basically 3 dimensions of the operational of the building, the performance, and how the mechanical system affects that performance. So, you know, the envelope is only one of the 3 things that I think about when I think about, you know, is it going to perform long term? But you're right, it's good to analyze both sides. That's why I would not leave the insulation out at the bottom. I would put something in that drains. Just risk management is all it is.
Totally, yeah.
Yeah.
No, I'm on board as well.
Yeah.
Cool.
Yeah, one of my favorite bits that came out of that NRC study was the idea that air and water have to be stopped at different planes.
Yes.
That is such a critical portion of that conversation, is ideally you've got, you know, a flange system or flashing at the window that you're actually stopping the air before it gets into that cavity. I think it's actually a bit of a misnomer that you even need to worry about the caulking on 3 sides. That if you've got a continuous interior seal, but you've stopped the air and you've got a water shedding surface to the outside, that inside still can manage it. As a matter of fact, there's probably some arguments about equalization of that chamber that actually come into play.
Yep.
So.
I agree. So if you think of the pressure drop, never have the pressure drop in the same plane as the drainage.
Yeah.
Right? Never.
To add to that, the last piece, you're relative to the lifespan of those building materials, potentially with the air vapor barrier on the outside, say relative to the 4-sided seal, you're using a peel and stick. The lifespan of that material might be 40 years, 50 years, whatever it is, in conjunction. So you're thinking the worst case, or the weakest link within that system, that building assembly. Moving into the interior, you're now relying on that entire assembly, relying on that bead of caulk, which potentially is a 20-year lifespan. So you've kind of reduced that entire assembly to be a 20-year assembly until maintenance needs to kind of come in, tear it out, and then recalc that. So
Yeah.
if you're looking at like CMU sort of 50-year assemblies, 100-year assemblies.
That's a different story. This is wood frame with
Right.
loose connected WRB. So if you're getting into peel and stick and you're peeling sticking all the way up, totally different discussion.
Okay.
Yeah, absolutely. I totally agree with you. Yep.
And I should know better than to only give you an hour. Yeah, we need to shut it down there. Thanks very much, Daryl. Really appreciate your coming out. Adrian's going to give us a couple of more exhibitors, and we're going to take a break until about 2:30-ish, and then we'll hear from Shiva. All right. Thanks, Daryl.
We'll wait until they're done. Yeah, let's do it.
Okay, good afternoon, everyone. My name is Kelsey Zadro from Omniglass right here in Winnipeg. We've been in business for over 40 years, supplying custom fiberglass profiles to the window and door industry, and also other industries that benefit from our material. We work exclusively with manufacturers and OEMs. We don't make windows or doors. Our focus is on the material, process, and performance. Over the past few years, we've expanded our customer base by over 30% as more customers move toward fiberglass to meet higher performance requirements and to deliver more value to our customers. And then about 18 months ago, we commissioned a new waterborne paint line, allowing us to be a one-stop shop. The line uses coatings from Superior Finishes, who is a local Winnipeg supply partner, who's also here at the show today. And we're breaking ground this year on a major facility that will expand our space by triple the square footage to support where our market is headed. At the end of the day, our role is straightforward: use material and manufacturing capability to solve problems and help our customers build better windows and doors. If fiberglass is a part of your roadmap or if you're evaluating solutions, we'd be glad to talk to you guys. Thank you.
Thank you.
All right. You ready?
No, I'm not ready. No one told me this was an on performance. I'm Stacy with Richelieu Glazing. We're pretty much distributors for like all your glazing needs. Preferred distributors for Amesbury Truth, so that's what I specialize in personally. Dan is our outside sales rep here, and yeah.
Awesome.
Thank you.
Thanks, guys. Fantastic.
Hi everyone, I'm Robert Pollock from Aribel Products. We are a distributor of components to the window industry. I think most of my competitors know who I am here. And I hope all the customers get to know, but we've got composite jambs, sills, hinges, stainless steel hinges. We've got now a new product, which is the first multi-point lock with a black faceplate. So come by, feel free to stop by, see what we've got, and I look forward to working with you guys. Thanks very much.
Thanks, Robert.
Do one more. Yeah.
Sure. One more. What a month.
Hi, everybody. I'm Brad Taylor. I work for Protective Packaging. We don't sell any packaging. We specialize in surface protection vinyl. We are the largest converter in Canada. We can convert any size down to 1/8 of an inch. We also specialize in double-sided tapes, foam tapes, and such. We work in many different markets, from the glass industry, PVC, stainless steel, anything that's manufactured and needs protection on top, that's what we do. Thank you.
Okay, great. Thanks very much. Okay, so we're going to take about 15 minutes. We're running a little bit long, so we'll cut this break a little bit shorter. So grab a coffee, water, whatever you need, and we'll see you back here shortly.